So if you ever find yourself standing in the exact center of a Category 5 hurricane, the sky overhead might actually be completely clear.
Yeah, it's wild to think about.
Right. You might literally see the sun shining or the stars twinkling if it's night and just feel this gentle breeze.
Exactly.
But just a few miles away from that completely peaceful spot, there is a natural machine generating more energy in a single day than our entire global electrical grid produces in that same time frame.
It's just massive scale.
It is. Welcome to the Deep Dive, everyone. Today we're opening up a really fascinating stack of meteorological research, oceanic data, and climate physics. We want to completely dismantle how you view these massive storms.
Yeah, we're gonna, strip away all the complex jargon and just look at the absolute fundamental mechanics of what makes them tick.
Because it really requires a shift in perspectives, doesn't it? When we see those satellite images on the news, it usually just looks like pure, unadulterated chaos.
Oh, for sure. It looks like an angry swirl of clouds that's just out to ruin millions of people's days.
Right, like a random act of atmospheric violence.
Exactly. But once you look at the underlying physics that we have here in the source material, that image of a chaotic swirl totally transforms.
You start to see it differently.
You do. You start to see a very precise, very powerful, and highly organized machine.
But before we get into how that machine actually operates, there's a quick naming convention thing we need to clear up.
Oh, the hurricane versus typhoon thing.
Yeah, exactly.
Yeah.
Because the data we're looking at covers hurricanes, typhoons, and cyclones. And honestly, for the longest time, I just assumed those were completely distinct types of weather events.
A lot of people do.
Right. Like I figured maybe a typhoon had more rain or, I don't know, a cyclone spun faster.
It's an incredibly common assumption, but meteorologically speaking, there is literally zero difference between them.
None at all.
None. They are all exactly the same atmospheric beast. The only thing that changes is the real estate.
So it's basically just a regional dialect thing.
Simply put, yeah. The overarching scientific term for the phenomenon we're looking at today is a tropical cyclone.
Okay.
So that's just a vast rotating storm born over warm tropical seas. If that tropical cyclone happens to form in the North Atlantic or the eastern North Pacific, it gets called a hurricane.
Got it.
But if it forms in the Northwest Pacific, it's a typhoon. And if you're down in the South Pacific or the Indian Ocean, near Australia, for example, they just call it a cyclone.
I love that. It's literally like regional names for soft drinks.
Oh, that's a good way to look at it.
Depending on where you travel, people call it soda or pop or Coke. They're completely different labels based on where you're standing, but it is the exact same bubbly drink in your glass. The flavor profile hasn't changed at all.
That is a perfect framework. The ingredients in the atmosphere are identical. Yeah. So understanding how a hurricane works means you automatically understand typhoons and cyclones.
Okay, that simplifies things for sure.
Right, but to really understand them, we have to throw away the idea that they're just, big storms.
Right, the research says there's something else.
Exactly. The fundamental thesis of the atmospheric science here is that a tropical cyclone is actually a heat engine.
A heat engine? Like a car engine.
In a very literal thermodynamic sense, yes. A heat engine is simply a system that converts heat into mechanical energy, or in this case, wind.
Okay, I'm following.
So a tropical cyclone is basically a machine designed by nature to draw vast amounts of warmth out of the ocean and convert it directly into kinetic energy.
Well, if it's an engine, it needs fuel, right?
Yeah.
I'm assuming the fuel is the warm ocean water.
You'd be right. Warm water is the baseline requirement. You cannot start this engine on a cold day.
Makes sense.
A tropical cyclone requires an ocean surface that's heated to at least 26.5 degrees Celsius.
Which is about 80 degrees Fahrenheit for those using that scale. Basically bath water.
Very warm bath water. But here's the critical part that most people miss. That warmth can't just be a thin layer baking at the very top of the water.
Oh, really?
No, that 80-degree heat has to reach down to a depth of at least 50 meters.
Wait, 50 meters? That's roughly 160 feet.
Right. It needs a massive, deep reservoir of heat.
But wait, why does the depth even matter? I mean, the storm is up in the sky. The air is only touching the very top layer of the ocean, isn't it?
Think about what happens when wind blows across a liquid. It creates waves, right?
Sure.
And it aggressively churns the water. As soon as a storm starts to develop and spin, those winds violently mix the ocean's surface.
Oh, I see where this is going.
Yeah, if that warm water is only a few inches deep, the storm's own churning will just pull up freezing cold water from the depths.
Ah, so it would essentially suffocate itself.
Exactly. It would kill its own fuel supply instantly. The cold water would hit the surface, the heat transfer would just stop, and the engine would stall out before it even really got going.
That makes total sense.
So that deep 50-meter pool of hot water ensures that no matter how much the storm churns the ocean, it just keeps pulling up more hot fuel.
Okay, so we've got our fuel tank, a massive, deep pool of hot ocean water. How does the engine actually fire up, though? Like, what's the spark plug?
The spark is a process involving something called latent heat.
Latent heat, okay.
It starts with the air just above that warm sea surface. The ocean naturally heats that air, and as we know, warm, moist air naturally rises.
Right, heat rises.
Exactly. And as this wet air travels upward into the cooler parts of the upper atmosphere, its temperature starts to drop.
And when wet air cools down, the water vapor condenses. Sort of like the water droplets forming on the outside of a cold glass of iced tea on a hot summer day.
That's spot on, and that condensation is the absolute core of the engine.
Really? Just water condensing?
Yep, because what we don't often perceive on a human level is the invisible energy exchange happening during that process. Think back to how that water became vapor in the first place.
Okay, the sun.
Right, the sun beat down on the ocean, using a massive amount of solar energy to evaporate liquid water into a gas. And that solar energy didn't just disappear, it was physically stored inside the water vapor.
Oh, so it acts like a battery. The water vapor is holding onto the sun's energy as it floats up into the sky.
That is a brilliant analogy, yes. And when that vapor cools and condenses back into liquid cloud droplets, that battery discharges.
Wow.
The scientific term for this is latent heat. It's the heat released when water changes from a gas back to a liquid.
So all that stored solar energy is suddenly dumped back into the surrounding atmosphere as raw heat.
Exactly. By forming a cloud, the air is literally heating itself up all over again.
That is wild.
And consider what warm air wants to do. It wants to rise.
Right.
So this newly released latent heat warms the air in the cloud, causing it to shoot upward at a much faster rate.
Almost like hitting the gas pedal.
Exactly. And as it rockets up, it creates an area of low pressure. Basically a giant vacuum down at the surface of the ocean.
Which act like a straw.
Yes.
Yeah.
Violently sucking up even more warm, moist air from the surface.
Which then rises, cools, condenses, and releases even more heat. It's a continuous self-feeding loop.
The warm ocean feeds rising air, the condensation releases latent heat, and that heat drives more air upward. Once that cycle gets organized, it continuously feeds itself.
Drawing immense, terrifying amounts of energy straight out of that deep water.
Exactly.
But, if this loop is so perfectly self-sustaining, what stops it?
What do you mean?
Well, if the ocean is the fuel tank and latent heat is the spark plug just continuously firing, why doesn't a hurricane just consume the entire atmosphere? Like, why does it ever stop growing?
Okay. Well, the engine actually has some very specific vulnerabilities.
Okay.
The most obvious one is its absolute reliance on that deep, warm water we talked about.
Right, the fuel line.
Exactly. The very moment a tropical cyclone moves over land or crosses into a patch of cooler ocean water, that fuel line is severed.
So no more warm, moist air.
Right. Without that constant intake of moisture to provide latent heat, the engine just sputters. Friction from the land tears at it a bit, sure, but the primary cause of death is simply starvation.
That makes a lot of sense. But right now, in our mental model, we just have this, giant invisible elevator of hot, wet air shooting straight up into the sky.
True.
Heat rising off a hot parking lot doesn't turn into a spinning buzzsaw. So where does the defining characteristic, the terrifying rotation, actually come from?
The spin is a gift from the rotation of the Earth itself through something called the Coriolis effect.
The Coriolis effect.
Yeah. Because our planet is constantly turning on its axis, anything that moves long distances across its surface gets deflected. It simply cannot travel in a perfectly straight line relative to the ground.
Oh, I've heard an analogy for this. It's like if you tried to draw a perfectly straight line with a marker on a vinyl record while it's playing on the turntable.
That's a good one.
Your hand is moving straight, but because the record is turning underneath it, you end up drawing a curved line on the label.
That is the exact physics at play. So in the northern hemisphere, the Earth's rotation deflects moving air to the right, and in the southern hemisphere, it deflects it to the left.
Okay.
Now, go back to that giant elevator of rising air we built. It's creating a massive vacuum of low pressure at the ocean surface, right?
Right.
And air is rushing inward from all directions to fill that void.
But because the Earth is spinning, that rushing air gets curved on its way to the center.
Exactly. As the air rushes toward the center, the Coriolis effect bends its path.
So in the north, it gets deflected to the right, which sets up a massive anti-clockwise rotation.
You've got it. And in the south, the deflection to the left creates a clockwise spin. That planetary nudge is what takes a disorganized cluster of rising thunderstorms and winds them up into a tightly rotating cyclone.
Now, the meteorological data we're looking at highlights a really bizarre geographic quirk about this spin, though.
Yeah.
Something about the equator.
The equator quirk is so fascinating. The Coriolis effect is very strong near the poles, but due to the geometry of a sphere, it actually vanishes completely right at the equator.
Completely. Like zero deflection.
Zero deflection.
Which means, logically, if there's no deflection to curve the wind,
Cyclones literally cannot form at the equator.
that is crazy. Even if the water's boiling hot, they just can't get their spin.
Exactly. If a storm tries to form right on the equator, the air just rushes straight into the low-pressure center. It fills the vacuum immediately.
So no curve, no spin, no cyclone.
Right. For the engine to organize, the storm needs to be at least 5 degrees of latitude north or south of the equator just to catch enough of that Coriolis effect to start winding up.
Okay, so we have the deep pool of 80-degree water, and we're far enough away from the equator to get a spin going. Are we guaranteed a hurricane now?
Not quite.
Yeah.
There is one final atmospheric condition required, and it acts as the great shredder of developing storms.
The shredder. Sounds ominous.
Meteorologists call it wind shear.
Wind shear.
Right. Wind shear is when the speed or the direction of the wind changes drastically as you move higher up in the atmosphere.
So they're blowing different ways at different heights.
Exactly. So the surface winds might be blowing gently to the east, but 5 miles up in the sky, the winds are screaming to the west at 60 miles per hour.
Okay, let me think about how that affects our rising column of air. It's almost like playing a game of Jenga,
Jenga. Okay, I'm listening.
where you spent all this time perfectly stacking those wooden blocks,
Yeah.
building this neat vertical tower of rising heat and moisture, right?
Right.
And wind shear is like someone walking by and just flicking the top block as hard as they can.
That is exactly what happens mechanically.
The whole stack tilts, loses its center of gravity, and falls apart.
Yes. The rising air is trying to build a vertical chimney to vent the heat. If there is high wind shear, the upper levels of that chimney get blown completely off-center.
And it just ruins the whole engine.
The heat gets blown away from the core, the pressure at the surface can't drop, and the storm just fizzles out into a disorganized cluster of rain clouds.
Wow.
So you have a true Goldilocks situation. You need water that is just the right depth and temperature, a distance from the equator that provides just the right amount of spin, and upper-level winds that are perfectly calm and uniform.
It is almost a miracle they managed to form at all when you put it like that.
It really is.
But of course, when those delicate conditions are met simultaneously, the storm organizes. And once it's fully formed, it develops a highly specific, deadly anatomical structure.
It does.
Let's walk through the anatomy of this monster for the listeners. Like, if we were to fly a plane from the absolute outside edge of a cyclone straight through to the dead center, what is the sequence of events?
Well, approaching from the outside, the first structure you encounter are the rain bands.
The rain bands.
Yeah, these are the long curved arms of heavy rain and squally wind spiraling outward from the center. You see them on radar as giant sweeping arcs.
Okay, so what does that feel like on the ground?
Well, they come in distinct bands, meaning you'll get hit with torrential rain and fierce wind for a bit, and then it might actually ease off slightly.
Giving you a false sense of security.
Exactly, only for the next band to sweep over you a little while later.
So you get this pulsing, rhythmic beating before the main event.
Right. And as you push further inward, that pulsing stops, and you hit a solid, continuous wall of absolute fury.
This would be the eye wall.
Yes. This is the eye wall. It's a ring of towering, dense thunderstorms completely encircling the center of the cyclone.
And that's where the actual heat engine is firing at maximum capacity, right?
Precisely. That is where the air from the ocean is rising the most violently. All that latent heat is being released in this concentrated ring.
So it's the worst part of the storm.
Without a doubt. Consequently, it's where the winds are at their absolute fiercest, and the rain is the most blinding. If you're on the ground, the eye wall is simply the most dangerous, destructive part of the storm structure.
But if you manage to push through that incredibly violent wall, suddenly everything stops. You step right into the eye.
The dead center of the pinwheel.
Yeah.
The eye is a region of profound calm. The winds drop to a breeze. The rain stops entirely.
And the skies often clear up, right? Like you can see bright sunshine during the day.
Sunshine during the day, or you look up and see the stars at night. You are standing in an eerily peaceful cylinder surrounded by a 360-degree stadium of towering black clouds.
I've always wondered why it's so calm in the middle of a literal atmospheric blender. Like, physically, how does that work?
Well, the physics of the engine actually force it to be calm.
Really?
Yeah, all that air rushing upward in the eye wall has to go somewhere when it hits the top of the storm. Most of it gets pushed outward, exhausting away from the storm,
Right.
but a little bit of it actually gets pushed inward toward the center and begins to slowly sink down the middle.
Oh, it sinks down into the eye.
Exactly. And as air sinks, it warms up and dries out. Sinking air suppresses any cloud formation, which basically acts like an eraser, just completely clearing the sky inside the eye.
You know, what really stands out to me here is the psychological torture of the eye. It is nature's ultimate false reprieve.
Oh, absolutely.
Because if you're sheltering in your house, the first half of the eye wall hits you. It sounds like a freight train. You know, trees are snapping, roofs are tearing off.
And then sunshine.
Exactly. The birds might even start chirping.
And the human instinct is to go outside, to check on your neighbors, to think the worst is finally over.
But it's a terrifying trick. Because if you step outside in that calm, you are literally standing inside the hollow center of a moving buzzsaw.
The storm hasn't stopped, it's still moving forward over the land.
Which means that peaceful eye is going to slide right past you and the back half of the eye wall is going to hit you.
And this is where the physics becomes structurally devastating.
Why is the second half worse?
Well, because the storm is spinning in a circle, the winds in that second half of the eye wall will be blowing from the exact opposite direction as the first half.
Oh, wow. I didn't even think about that.
Yeah. So a tree or a power pole that was pushed to its absolute breaking point, leaning south for 2 hours, suddenly gets slammed with maximum force leaning north.
So it's that back and forth whiplash.
Exactly. That reversal of pressure is what causes so much infrastructure to finally just fail.
Well, with winds that fierce and the structure that destructive, it makes total sense that we rate these storms based on their wind speed.
Yeah.
I mean, we hear about Category 1 through Category 5 storms constantly on the news.
We do. And the Saffir-Simpson hurricane wind scale is immensely useful for meteorologists to categorize structural wind threat.
Right.
But relying on it exclusively to communicate danger to the general public can actually be deeply misleading.
Really? Because I always just assumed a Category 5 was objectively the worst-case scenario, and a Category 1 was just, a bad thunderstorm.
Well, in terms of wind tearing off shingles, yes. The scale is based purely on maximum sustained wind speed.
Okay, so what's the flaw?
The flaw in our public perception is that wind is rarely the thing that kills the most people in a tropical cyclone. The water is.
The water.
We fixate on the wind speeds rattling our windows, and we completely forget about the ocean.
Okay, so what exactly is the ocean doing while the wind is blowing?
When a cyclone is churning toward the coast, those massive, sustained winds act like a bulldozer across the surface of the sea.
A bulldozer?
Yeah, they physically pile the ocean water up ahead of the storm into a giant elevated dome. And when that dome of water surges ashore, it's called a storm surge.
Ah, right, storm surge.
And we aren't talking about, big surfing waves here. We're talking about the actual sea level rising by 3, 4, or even 5 meters in a matter of minutes.
A 5-meter rise in sea level? I mean, that's a 2-story building.
It is.
That's just a drowning wall of seawater moving inland, completely swallowing streets and homes.
It is. Historically, storm surge is the ultimate threat. It is the biggest cause of loss of life. And the category scale, being based only on wind, doesn't always capture this threat.
Because a low-category storm could still push a lot of water.
Exactly. A massive sprawling storm might only have Category 2 winds, but because it's so incredibly wide, it's pushing a mountain of water ahead of it that rivals a Category 4.
And it isn't just the ocean water that makes the category scale misleading, right? The sources also mention the rain threat.
Right. If a cyclone is moving very slowly across the land, it acts like a giant stalled fire hose.
Just dumping water in one spot.
Yes, it can dump sheer, incomprehensible volumes of freshwater rain over a span of days. This causes catastrophic inland flooding well out of reach of the storm surge, and long after the extreme winds have actually died down.
So using only wind categories to communicate the danger, it's like rating how dangerous a car crash is solely by looking at the speedometer.
That's an interesting way to put it.
Right, but it completely ignores the fact that the car is currently driving off a cliff into a deep lake.
Exactly.
A so-called weaker Category 1 storm that is incredibly slow, holds a massive amount of rain, and hits a low-lying coast at high tide. that can be a far worse disaster for a community than a fast-moving, dry Category 4 that just quickly blows through.
You nailed it. A single number categorizing wind simply never tells the whole story of a storm's destructive potential. Water is the heavy hitter.
Which leads us to a very natural, if pretty unsettling conclusion.
Okay.
You mentioned earlier that the engine dies when it runs out of 80-degree water.
I did.
Which makes me wonder, if global temperatures are pushing ocean heat deeper and wider, are we essentially building a bigger fuel tank for these things?
We really have to look at the thermodynamics here, and the research notes a very interesting distinction on this point.
Okay, what is it?
The data does not definitively show that we are getting more tropical cyclones overall.
Wait, really?
Yeah. The total number of these storms globally each year is relatively stable. In some specific regions, it might even decline slightly.
So the atmosphere isn't just firing out dozens of extra hurricanes every season. That's at least some good news.
No, the frequency isn't the primary concern. The real danger lies in the physics of the storms that do manage to form.
Because of the larger fuel tank.
Exactly. Because we have measurably warmed the oceans, the global reservoir of heat is deeper and hotter. There is simply more high-octane fuel available for a storm to tap into.
And with a larger fuel tank, the engine can rev higher.
Exactly. It means the strongest storms are much more likely to achieve higher maximum intensities.
And what about the water side of the equation? Like, does a warmer engine mean a wetter storm?
Yes, because warmer air physically expands and has the capacity to hold more moisture.
How much more?
The established rule in atmospheric physics is that the atmosphere holds about 7% more water vapor for every 1 degree Celsius of warming.
7% more per degree. I mean, when you're talking about storms the size of Texas, that is a massive increase in the payload of those clouds.
It dictates that when the cyclone's engine finally condenses that vapor, it results in significantly heavier rainfall rates. The flooding potential scales up dramatically.
And then finally, there's the changing baseline for the storm surge.
Right, because global sea levels are rising overall.
So every single storm surge is now starting from a higher baseline.
Exactly. If the ocean off the coast is already several inches higher before the storm even arrives, that dome of water is pushed that much further inland.
It inundates streets and neighborhoods that might have previously been just out of reach.
It does.
So to put it in perspective for someone living on the coast, it isn't necessarily that the atmosphere is firing a machine gun with more bullets. It's that the bullets themselves are getting bigger, heavier, and doing much more damage when they hit.
That is a stark but very accurate summary of the physics. The current consensus points to a higher proportion of severe storms that carry more water and ride in on higher seas.
And this distinction is absolutely critical for vulnerable coastlines, right? Like the massive stretch from Queensland all the way around to the northwest of Western Australia.
Yeah, absolutely. They live in the path of these engines every single summer. And understanding that the mechanics are shifting really dictates how they must build and evacuate in the future.
It changes everything about how we prepare.
It has to.
Well, let's bring this all together for you, the listener. The next time you see a satellite image of a vast, slowly turning pinwheel on the Weather Channel, you aren't just looking at random chaos.
Right.
You aren't looking at some malevolent tantrum of nature.
You're looking at one of the largest, most powerful natural engines on the planet.
A machine.
Yeah, a machine that is quietly, relentlessly turning the warmth of a summer ocean into wind and rain, governed entirely by the beautiful, unbreakable laws of physics.
And knowing about the latent heat battery, the Coriolis spin, the deadly wall of the storm surge, and that false piece of the eye, it doesn't make the storm any less awesome.
Not at all. By removing the mystery, we replace fear of the unknown with a healthy, informed respect for the mechanics of our planet.
It gives you the exact tools you need to understand the true threats behind those sensational weather headlines.
Exactly.
But, reading through all this data, it does leave us with one really provocative question to mull over.
Oh, yeah.
If tropical cyclones are essentially giant, natural heat engines designed by physics to draw excess heat out of the ocean and vent it away into the upper atmosphere.
What happens to the Earth's delicate global temperature balance if a change in climate alters where and if these massive natural cooling engines can form in the future?
Right. If the ocean can't vent its heat through these storms, where does that heat go?
It's a huge question.
Something to think about the next time the wind starts to howl.